mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Good morning. Welcome back to grade 12 physics online edition. I hope you all enjoyed your spring break and were able to spend some time with family and enjoy some of the nice weather we had prior to the snow coming. And now you're ready to get back at it for the next 4 days ahead of spring break. By now you've probably already heard that they announced last week that in-class learning would be suspended until further notice. And so we'll be doing this online thing for a while longer. It's indefinite. We don't know when we'll be back in class. Hopefully it'll be sooner than later. But in the meantime, we'll continue doing this. And it seems to be working all right. And again, if you ever have any questions, feel free to phone or email in your questions, and I'll always answer them in another video as required. And we want to continue doing some video chats as well, just to keep connected as we continue through this model. All right, before spring break, we were talking about energy, and we were looking at the conservation of energy. And we had our kinetic energy, which was our energy of a moving object, 1/2 mv squared. And we looked at elastic potential energy, and the fact that when we use force to deform, to stretch, or compress the spring, the work done there is equal to the potential energy that's stored in that spring, and then that energy can be transferred into kinetic energy. And we learned about the law of conservation of energy, and that energy is not created or destroyed in any interaction. And so when we have potential energy stored in a spring, all of that potential energy gets transferred into kinetic energy as the object is moving. All right. Today, we want to look at gravitational potential energy, so we're going to get right into it. And last week, we learned that the work done to deform a spring equaled the elastic potential energy that was stored in the spring. Today, we want to look at gravitational potential energy, and the concept is the same. The work done to lift an object is equal to the change in gravitational potential energy. Now, the word change here is different. We don't have a change in elastic potential, but here we have a change in gravitational potential. And that's simply because when I have an object that is a certain height off the ground, it's got a gravitational potential energy. But I can lift it to a new height, and that gives me a different value of potential energy that's stored in this textbook. Okay? And so we always want to sort of take a zero level, a line that we're going to make zero, and then we're going to go up from that point. And so we're lifting objects to new heights, and that creates more potential energy in it. And again, potential energy is the ability to do work. And so it should make sense to you that the higher an object is, the more work it's going to do on something when it falls, transferring all that gravitational potential energy into kinetic energy. All right. Work, as we know, is force times displacement. In this case, our force is the force of gravity. To lift an object, we have to lift with a force that is at least equal to the force of gravity. And we're going to change d into h, because now it's height. We're lifting to a certain height. And so when we do a little formula substitution, force of gravity is mass times our gravitational field constant times the height. And so mgh becomes our formula for gravitational potential energy. We'll call that Eg for energy, gravitational, and it's simply equal to mgh. All right, we're ready to do some sample problems because this is the formula. We have our other two formulas for kinetic and elastic. Now we have a new gravitational one. Now the challenge is combining them together. At the end of last week, you did a few questions that had things that were compressing or stretching springs and then being transferred into kinetic energy. Today we're going to combine all three together. Today we'll probably just combine gravitational and kinetic, but as we move into this week, we'll do more that will combine all three things together. Let's head on over to the other board. We've got a sample problem ready to go. All right, here's our sample problem. We have a ball that has a mass of 0.25 kilograms. It's going to be thrown vertically upwards from the roof of an 18-meter high building with a velocity of 16 meters per second. the ball's going to go up and it's going to come down, and it's just going to miss the edge of the building on the way down, and we want to find some pieces of information about this. So here's our diagram. We have this diagram here. We've got our 18-meter high building. We've got our ball that's being thrown upwards, reaching a certain height, coming back down. The first thing we want to find is to what height does this ball rise? Now, some of you will recognize this as a question we would have done in our kinematics unit either last year or even earlier on this year with projectile motion. So we can do this question using strictly kinematics, but we can also do it using the law of conservation of energy. What we have here is that at any point on this diagram, okay, whether it's here at the beginning, whether it's here at the top, or here at the bottom, or anywhere in between, there's a total amount of energy that this system has. And so by looking at the total amount of energy and recognizing that that total amount of energy has to remain constant, we can solve things fairly quickly. And so what we're going to do is because we want, in this first question, to what height does the ball rise, we have a starting point. I'm going to call that starting point A, and I'm going to call our highest point here B. All right? And so we're always going to have a total amount of energy. All right, and that total amount of energy at A has to equal the total amount of energy anywhere in this system, but for this case, we're going to look at point B. All right, at A, what types of energy does the ball have when it's sitting here at A? And it's not sitting, it's moving at 16 meters per second. So it has a kinetic energy at A, but it also has a gravitational energy because it's 18 meters off the ground. So the total amount of energy that the ball has at point A is its kinetic energy, because it's moving 16 meters per second, and it's off the ground 18 meters. At point B, now it has to equal, right? Because energy can't be created or destroyed, so all of the energy has to be transferred. Well, at B, it comes to a stop when it gets to its highest point. If it comes to a stop at its highest point, it doesn't have any kinetic energy at that point because it just stopped. But it's off the ground, which means it has gravitational energy. And so our formula becomes this. The kinetic energy plus the gravitational energy at A has to equal the gravitational energy at B. And now if we just fill in our formulas, we'll have 1/2 mv squared plus mgh equals 2mgh. Now this is the height at A, this is the height at B. It's important to remember that those two h's are not the same. But what you will notice is that there's a mass in each of the three terms, and that mass is the same. It's the same ball. Mass 0.25 kilograms, and so we really don't need the mass of this ball. So we can cancel out the mass. In this case, we don't need mass, and that will happen often in questions that are gravity and kinetic energy combined, because there's math in both those equations, or mass in both those equations. There's a lot of math there as well, but there's mass in both of those equations, and so they will often cancel out when you put them together. All right, our goal here was to solve for how high the ball went, which was HB, and so we can do that now. We can plug in our information. We've got 1/2 times 16 squared plus 9.8 newtons per kilogram times 18 meters has to equal 9.8 newtons per kilogram times the height at B. And of course you can plug that into your calculator, and if you do so, you will get the answer of 31 meters. So H equals 31 meters. All right, so it's nice and simple. It's a quick calculation. It is a little quicker than the kinematics, but not much. So really, take your pick, kinematics or energy. But the second part of this question, and I'm not going to write it out, I'm just going to talk about it, but the second part of this question could be, with what speed, with what velocity does this ball hit the ground? And if we were to do that, let's call this point C at the bottom here. Okay, we're just going to change some of our equation here. Okay. If it was what's the speed with which it hits the ground, we would now say, well, we still have a total amount of energy at A that we know, but now, when it gets to point C, it doesn't have any gravitational energy, it only has kinetic energy. And so all of this energy, again, that it had at the beginning, is now going to be equal to the kinetic energy at C. And we do it the same way we just did the last question. We can plug in our values. Again, the mass will cancel out, and we can plug in our values, and we'll be left, the only thing we won't know is the velocity for this kinetic energy. And we can solve for that velocity. And so it becomes fairly straightforward. Okay, we can do the same thing right here. Right? If we said find the velocity at this point, we'd have to determine a height here. We'd have to tell you a height, say at 12 meters above the ground. Well, at this point here, well, again, it's got kinetic energy because it's moving, but now it also has a gravitational energy. So our left-hand side of the equation wouldn't change. We still have our kinetic energy and our gravitational energy at point A. And now we'd have this point here where, again, it has kinetic energy and it has gravitational energy. Okay, so all that would mean plugging in and adding another gravitational energy to that point. Okay, gone through this a little bit fast, but you can, again, rewatch this over and over again. But the point is that there is a total amount of energy before and after, okay, the interaction. And those always have to equal. And so we take 2 points. We take a point A where we know all the information, and we take another point where maybe we're missing some information, but we make them equal to each other, and then we're able to solve. All right, and finding the velocity at the bottom here using kinematics takes a couple of steps, whereas if you do it using energy, it's again 1 step, and it's always going to be this formula. Okay? It's just a matter of what we have. And what you could do, because this is only kinetic and gravitational, we know that it's always going to be EK plus EG equals EK plus EG, right? At various points, wherever you want to pick a point, right? So it could be B and C, it could be A and C, A and B, whatever you choose, whatever works, that leaves us with 1 unknown to solve for. And at certain places, some of these are 0. Right? So when we're looking at the highest point, the kinetic energy is 0. When we're looking at when it hits the ground, the gravitational energy is 0. And so pieces disappear depending on where we are in this situation. Okay? One of my favorite questions, that you'll probably get one in your assignment today or tomorrow or very shortly, is roller coaster questions. And roller coasters start at a point where you go up to a height and then they come down and go through their ups and downs, loops if there is, etc. And you can solve velocity and height questions with roller coasters using the same concept. Find a point where we know the information, right? So we know the total amount of energy. That total amount of energy has to remain the same as we go through questions. All right, so you're going to get a textbook, an assignment today on a handout, so you can check Connect for that. It'll be out of your blue textbook. There are 6 questions on it. I want you to give them a try. Tomorrow, when we come back, not going to be a new lesson. We're going to be doing more questions. I'll go over some of the questions that you'll have done today from this handout, and I'll be assigning some more questions. So if you don't get all 6 done, that's not the end of the world. Try them so that we can, when you go over them, they make sense. And know that you're going to be getting a few more questions as this week rolls on. Again, it's a 4-day week, so it'll be a little short. We have Friday off, it's Good Friday, and then Monday is an administration day. And so there'll be no school on Monday as well. So as we leave today, I do want to remind you that yesterday was Palm Sunday. And Palm Sunday, yesterday we were reminded in church that as Jesus was entering Jerusalem, the crowds were laying down palm branches in their coats in the streets and yelling and cheering, Hosanna, Hosanna, King of Kings, Lord of Lords. And those people had certain expectations for Jesus. They expected him to come in and to take over and become the King of all kings. And they expected him to do that forcefully. Well, Jesus totally changed that. He by far exceeded their expectations. Now, they couldn't see that in the short term, but in the long term, we could see that Jesus far exceeded the expectations that the people had for him. And so I just want to remind you that today that Jesus is The King is the Lord that will exceed your expectations. And so no matter what your expectations are going forward in terms of school, in terms of your future, in terms of where this is all going with this virus, know that Jesus is the expectation exceeder. He will exceed all your expectations, and he is the King of Kings and Lord of Lords. And so I wish you a good day, and we'll see you tomorrow.